Good morning, Townview. So today we're going to be talking about acids and bases, and we're going to start by defining acids. We'll start by defining these acids and bases. So first of all, top of your page, you're going to write down acids and bases. That's going to be our title. And then, as you can see, it says properties of acids and bases, but we've already discussed these. So for the people who haven't been here, here are the properties. Go ahead and write these down. Next up, you have your properties of bases. Go ahead and write these down. I know y'all did. People who aren't here are the ones writing this stuff down. All right, so now we're going to get into our definitions. So the first definition you're going to need to write down is Arrhenius's definition. So Arrhenius, this is a scientist, and his definition of an acid is going to be anything that generates H plus in solution. So what does that mean? We talked about how salts, when you put them in water, they dissociate to form anions and cations. For example, NaCl. When we put this in water, it's going to form two ions. It's going to form Na plus, and it's going to form Cl minus. These are the two ions that it forms when you put it in water. Now, acids, when you put them in water, they do a very similar thing. So HCl, hydrochloric acid, when we put it in water, it's also going to generate ions. It's going to generate H plus, and it's going to generate Cl minus. Now, Arrhenius's definition is an acid is anything that if you put it in water, it generates H plus. So HCl falls under Arrhenius's definition of an acid. H plus is referred to as hydrogen ion. You already know this. So hydrogen ion is just an H plus. Now another way you could see it written down is going to be H3O plus. So if we put HCl in water, water is H2O, and we put HCl in water and it forms all these H plus ions and these Cl ions. What also happens is the water is going to bond to these hydrogens, forming H3O plus. And H3O plus is hydronium. So you need to write this one down. You need to know what hydronium is. So hydronium, that's just water bonded to an H plus, and you get hydronium by putting acids in water. But just know H3O plus and H plus, they act the exact same way. They're the exact same thing. The only difference is how we're writing them down. So this one is not attached to a water. This one is attached to a water, even though they're both in water. Yes, ma'am.
How do you know if how do you know if a solution makes H plus? Like,
Well, if it becomes acidic, it's forming H plus. So ways we could test it is we put it in pH paper, and pH paper changes color. So we talked about litmus paper on last class. Y'all remember litmus paper?
yeah.
So you put it in a liquid, it goes red. That means you're forming H plus. That means you're dealing with an acid.
Yeah, but what is on the test? So like,
So on the test, are you asking how you can identify an acid?
yeah, I guess so.
I'm not sure. Like the type of question that you're asking is not a type of question I'll ask on the test.
So, okay.
So I wouldn't be too concerned about it. But basically, take a look here. So here we have HA. What is HA? When you see H, that means hydrogen. This is H plus. And then A is just the other part. So it could be Cl, it could be Br, it could be F, it could be anything. That's what HA is. So HA is a variable for an acid. When we put an acid in water, what's it going to form? It's going to form H plus, because we already know about H plus, and it's going to form an anion with the negatively charged anion. So this is the formula that you want to know. All right, next up we have Arrhenius's definition of a base. So a base generates hydroxide, or OH, in water. Y'all remember hydroxide? It's a polyatomic ion. It's on your sheet. We've been using it all year. So when you put a base in water, it's going to form OH minus. OH is known as hydroxide ion. Go ahead and write that out. And then here you can see BOH. BOH is just, it's a variable for any base. And the bases are going to form OH in solution. So the next definition we're going to need to learn is going to be Bronsted and Lowry. So Bronsted and Lowry is just another couple of scientists who also worked with acids and bases. And Bronsted and Lowry's definition of an acid, and this is what you're going to write down: any substance that donates a proton to another substance. Any substance that donates a proton to another substance. Now, when they say proton, what are they talking about? They're talking about hydrogen, because what is hydrogen? Hydrogen is just a proton with a single electron. So it's got one proton, one electron. That's what a hydrogen is. So any substance that donates a hydrogen. So the definition here is not very different, specifically for acids. So Bronsted and Lowry's definition of an acid is it's the exact same as Arrhenius's definition of an acid.
Give us a worksheet on it. We had a conversation.
Well, that worksheet was just an introduction and didn't require that you know this. All right, let's keep going. Now, Bronsted-Lowry. So on your page, you should have written down Bronsted and Lowry, and we just wrote his definition of what an acid is. Next, we're going to write our definition of what a base is. So it's any substance that receives a proton. Now, this is where it's different. So in the case of Arrhenius, he says that you have to have a hydroxide, an OH. For Bronsted-Lowry, he says anything that accepts a hydrogen. So that doesn't necessarily mean hydroxide. So an example is going to be something like NH3. So NH3 is going to have a minus charge. And if there was a proton nearby, what's it going to do? It's going to take that proton and it's going to form NH4. So the difference between Arrhenius and Bronsted and Lowry is Arrhenius says hydroxide only, and Bronsted-Lowry, they say anything that accepts a hydrogen. So their definition is for an acid, this is going to be a proton donor. And then for a base, what's it going to be? Proton acceptor. So y'all have heard this before. For Arrhenius, you have to have an H plus over here, and then you have to have an OH minus over here. So that's the difference. So Lewis acids, you don't have to worry about Lewis acids. Don't worry about these. But if you can see here, all Arrhenius acids are Bronsted-Lowry acids. It says acid here. This should say base. Because acids are really the same for both. And it's the bases where you're going to see the difference. So all Arrhenius bases are Bronsted-Lowry bases, but not all Bronsted-Lowry bases are Arrhenius bases, because you have to have an OH here. And then here you could have something like NH3 minus. So anything with a minus charge would be considered a Bronsted-Lowry base. All right, let's move on. So what is an acid? We should have already written this down. An acid is a proton donor. So a proton donor. And then what is a base? It's a proton acceptor. Bless you. All right, next thing I want you to write is going to be conjugate pair. So conjugate pair. What is a conjugate pair? It's what something turns into after the reaction happens. We'll talk about them more on the next slide. But after a change has occurred, what you're left with is going to be your conjugate. Okay, let's keep going. All right, so here's an example of a reaction. Anytime you see these arrows going back and forth, so since the beginning of the year, we've been showing one-way arrows. A one-way arrow is telling you this is a one-way reaction. For example, if you burn something, there is no going back in that reaction. So that would use a one-way arrow. When you see a two-way arrow, what you need to know is this reaction is going back and forth. So yeah, it's moving back and forth. So over here we have HA. That's going to be our acid. It could be any acid. It could be HCl. It could be HF. I'm just going to put HF. And then we have our base. So here, water is considered a base. So Bronsted-Lowry's definition uses water as both an acid and a base. So in this scenario, water is acting like a base. What happens when we put acid in water? We already talked about how it dissociates, forming H+ ions. And we already talked about how sometimes these H+ ions are going to bond with water, forming H3O+. What do we call H3O+? Hydronium. And then we're left with A+. What is A+? Or sorry, A-. What is A-? In this scenario, what is A-? So what is A-? So we started with HF. Our H+ went here. So what's A- going to be? All right, so in this scenario, it's going to be fluorine. So it's going to be fluorine ion. Over on this side, this was our acid. On this side, it's going to be our conjugate base. Now, what's this one going to be? So, all right, conjugate acid is right. So H2O used to be our base. Now it's going to be our conjugate acid. What does that mean? It means H3O+, that's the acid now. And then it means F-, that's our base now, which means this becomes our proton acceptor and this becomes our proton donor. So in a Bronsted-Lowry definition, they shift over when the reaction occurs. But it's a reaction that goes both ways. So it goes backwards and forwards, and you're going to have both acid and conjugate acid, base and conjugate base in the solution all at the same time. Here's an illustration of it. All right, let's keep going. All right, so the acid on one side reacts to become the base on the other side. So over here we have another reaction. We have HCl, and we know HCl is going to be our donor, and it's going to give a hydrogen away. Now NH3 is going to act as our base, which means it's our proton acceptor, and it's going to take that proton, forming NH4+, and then Cl- becomes our base over on this side. So over here you can see that we're starting with an acid. Over here it becomes our base, and then here we have a base, and then here it becomes our acid. And this is over on this side, these are going to be both of our conjugates. So conjugate acid, conjugate base. All right, so let's go ahead and work out some problems. So what are the acid-base pairs in these equations? So let's take a look at the first one. So we have HCl plus H2O. Which one is our acid? So this is our acid. What's H2O going to be in this scenario? This is going to be our base. Now over on this side, H2O becomes H3O+. So what is it now? Now it's our conjugate acid. And then what's Cl-? That is easy, right? All right, next one. We have NH3 and we have H2O. So sometimes it's easy to see what's what just by looking at the reactant side. But the best thing to do is to look at how things change. So here we have NH3. Over here we have NH4. So what did NH3 do? Did it donate or did it accept? It accepted a proton. So what does that make NH3? So this is our base. H2O did what? It gave a proton. So what does that make H2O? So H2O is our acid here. And then NH4 plus is going to be what? Conjugate acid. And then OH. Now, y'all could be chemistry teachers too. All right, so let's go ahead and do this practice. I'm going to give you guys, let's do 3 minutes. I want you to solve all of these. So it says write the conjugate base for the following acids, and then write the conjugate acid for the following base. I don't want to tell y'all what to do. I think y'all know what to do. So let's go ahead and see if we can get it on our own. So for our first one, 1 second. All right, so for our first one, what happened? We gave up this hydrogen, and then it became ClO4, and now it's got a minus charge. So don't forget the charge. That's the important part. All right, next one. What's it going to become? Is it just PO4 minus? How many hydrogens is it going to lose? It should only lose 1. So this becomes H2PO4 minus. Because now it needs a hydrogen to be balanced. It's unbalanced. If we calculate the net charge, you'll find that there's an extra, it needs another proton to be balanced. Yes. Let me show you why. So if we have something like HCl, so this has a minus, so chlorine has a -1 charge, and then hydrogen has a +1 charge. So what's the net charge? It's got a net charge of 0. Now, if we take the hydrogen away, chlorine is going to have what charge? It's going to have the minus charge. So when the hydrogen is gone, it becomes negatively charged. If you remove 2 hydrogens, it becomes -2. If you remove 3 hydrogens, it becomes -3. All right, let's keep going. Next one should be CH3NH2, and then all it did here was it lost the plus charge. So this was a conjugate acid. So this was a conjugate acid, and we just turned it into a regular base. It's either going to be the first one or the last one. You always take the first one. If there's not a first one, you take the last one. There is no hydrogen. By first one, I mean in the beginning, like here. CH3?
Oh yeah, what's CH3?
It's a molecule.
Oh.
So these hydrogens don't want to detach from the carbon. Carbon doesn't give up hydrogens easily. Nitrogen will more easily give up the carbon, and the reason for it is because of the periodic table. So this is more electronegative, so it's got a stronger pull on the hydrogens. Those are just easier to give away, the ones attached to the nitrogens. All right, so let's go ahead and take a look at the next one. So conjugate acids for the conjugate base, or sorry, for the following bases. So CN minus becomes what? HCN, good. And then H2O becomes what? H3O what?
H3O plus.
H3O plus.
Right?
Bases gain hydrogens, yes. They're proton acceptors. Yeah, so if you gain a hydrogen, you become more positively charged. If you lose a hydrogen, you become negatively charged. All right, let's keep going. All right, here, all we're doing is we're labeling these. So I'm going to let you guys do these on your own. You don't have to write them out, just label them. So acid, comma, base, comma, conjugate acid, comma, conjugate base. I don't know if that's right, but that's what you're doing. So let's do all 3. I'm going to give you guys 3 laps. That's really all you need, and then we'll go over them. All right, so let's go ahead and take a look at H2O. So H2O becomes what? OH minus. So what did H2O do here? It gave away a hydrogen. So what does that make H2O? This is our acid, which means this is our base. And then over here, you're going to have your conjugate base. And then here, you're going to have your conjugate acid. These are what the questions are going to look like on the test. If this is easy, then you're going to get a couple questions right. There's going to be at least 2 of these. All right, let's look at the next one. So over here, we have H2O. And here we have OH. So what does the OH do? This one's actually simple. So OH is always what? OH is always a base, which means this is going to be our acid, and you know that because it's got that hydrogen. And then here H2O is going to act as what? It's going to be our conjugate acid, and then here we have our conjugate base. So what I wrote up here ended up being right. So H2O becomes H3O plus. So this is our base. This is our conjugate acid. This is our conjugate base. And then this is our acid. Like, I just throw stuff randomly and I got it right. Like, these are really easy questions. What it's most likely going to look like is it'll show you a reaction. It'll ask you, what is this? And then you just got to label it. Acid, base, conjugate base. All right, let's keep going. So next up, we have neutralization. So you have to be able to predict neutralization reactions. Let me read the T for you. Predict products in acid-base reactions that form water. All right, so first I want you to write neutralization. What does neutralization mean? A neutralization reaction is anytime you mix an acid and a base. So it's a chemical reaction between an acid and a base. And what's nice about neutralization reactions is they always produce the same thing. So here we have HCl, and here we have NaOH. This is the simplest type of reaction you're going to see. And HCl, when you put it in water, what ions is it going to form? HCl, when we put it in water, what 2 ions are going to form? All right, H plus and Cl minus. And then here we have NaOH, sodium hydroxide. When we put this in water, what's it going to form? And then what else? OH minus. Now, this neutralization reaction, it's basically a double replacement, but we always call them neutralization when it's an acid combining with a base. So this H plus is going to bond with this hydroxide, forming what? What's OH plus H plus? It's going to be H2O. And then Cl minus is just going to bond with the Na. So Cl minus and Na are going to bond to each other. What are they going to form? NaCl. So anytime you take an acid and a base, you're always going to form the same 2 things. You're going to form water, so H2O, and you're also going to form a salt. So the products of neutralization are always salt and water. It's kind of crazy. The ocean's full of salt water. When I say salt, though, I don't mean this salt, which is edible salt. It could be any kind of salt. What is a salt again? It's a metal and a non-metal. It's an ionic compound. So salts are just ionic compounds. It could be NaCl. It could be CaBr2. It could be K2O. It could be any of these salts. It doesn't have to be this particular salt. But what you're going to form every single time is salt and water. All right, let's keep going. So salts can be neutral, they could be acidic, or they could be basic. When we say neutralization, we don't mean that it's got a pH of 7. So our acid, so here we have a strong base. So let's say this has a pH of about 12. And here we have a weak acid. So let's say we have a pH of about, let's say 6. If we combine these two things together, they're not going to create something that's neutral. Neutral would be a pH of 7. What do you think the pH is going to be if we combine a 6 with a 12? Same quantity. Is it going to be more basic or more acidic? So here's our pH scale. Let's draw out the pH scale. So it goes from 0 to 14. 7 is right here. And then we're combining a 12. So 12 is right here. And then we're combining it with a 6, which is right here. So what's our resulting pH going to be? Is it going to be acid or base? It's going to be base. So it's going to be somewhere between the 6 and the 12, which is going to be about right here, which is, we could call this an 8 or a 9, let's say 8.5. So our pH is still going to be a base, still going to be basic. It depends on what acid and base you're combining together and the quantity, how much of it you're putting in. But just know, just because you just saw a neutralization reaction doesn't mean that your pH is 7. All right, let's keep going. All right, now we're going to talk about acid and base strength. So there are strong acids and there are strong bases. I want y'all to write these down. These things you actually have to memorize them. I don't make y'all memorize a lot, but here are your strong acids and here are your strong bases. I'm going to give you a little bit of time to write them out because you have to be able to identify these. Yeah, they're not. All right, so we all wrote down our strong acids and our strong bases. Now let's talk about what that means. So a strong acid and a strong base, this applies to both of them. What you need to know about them is they completely dissociate. So this you want to write down. Strong acids and bases, they completely dissociate in water. What does that mean? It means when you put hydrochloric acid, if we take HCl and we put it in water, then let me show you mathematically, actually. If I take 1 mole of HCl and I put it in water, what's going to happen? So you're going to have 1 mole of H plus, and then how many moles of Cl minus? How many moles of Cl minus? 1 mole of Cl minus. Will I have any HCl in that water? Will I have any HCl in that water? No. So you might have just a little bit, like less than 1%, but it's going to fully dissociate in water, which means you don't have any of the original product. And what makes this strong is all the free hydrogen ions that are just floating around. That's what makes strong acids so strong. They fully dissociate in water. 100% of the HCl is going to turn into H plus and Cl minus. Now, how is that different for weak acids? So a weak acid, here we have HB. Well, let's say HF. So here's hydrofluoric acid. If I put 1 mole of hydrofluoric acid in water, how much of it is going to turn into H plus? We're going to have about 0.1 moles of H plus. How many moles of F minus? How many moles of F minus? 0.1 moles of F minus. How many moles of HF will I have in the water? It's going to be 0.9 moles of HF. Does that make sense? So over here we get full dissociation, and then here we get partial dissociation, about 90%. So for weak acids and bases, what you're going to write is partially dissociate in H2O, about 10% dissociation. So 10% of it turns into H plus and whatever your conjugate base is, and 90% is going to stay the original acid or base that you put in the water. So a strong acid is how many times more powerful than a weak acid? It's 10 times more powerful. 10 times more hydrogens in the water, so it's 10 times more powerful. Any questions on what a strong acid is? All right, I'm going to change the screen. I want to see what y'all think. Don't read it off your journal. What is a strong acid? Completely dissociates in what? In water. Good. What is a weak acid? Partially dissociates. How much dissociates? About 10%. How much stronger is a strong acid? 10 times stronger. That's really what you need to know about strong acids and bases. Now, you're also going to need to know which ones are the strong acids and bases. You could get a question on identifying which one is a strong acid. Like the ACP always does that. Which of these is a strong acid or a strong base? And then you just got to circle the one that is. All right, so let's do some practice. Write out the balanced equation for the neutralization reaction between hydrobromic acid and barium hydroxide. I'm going to give you guys 4 laps, and then we'll go over this one. Bless them. All right, so we're writing a balanced equation for the neutralization reaction of hydrobromic acid and barium hydroxide. So hydrobromic, it starts with hydro. What does that mean? That means it's binary, and because it's binary, that means you just have a hydrogen that's going to be bonded to a bromine. Hydrogen has a charge of +1, and then bromine has a charge of -1, which means you only need one of each. So it's going to be HBr plus barium hydroxide, that's going to be Ba, which has a charge of +2, and then OH, which has a charge of -1. So how many hydroxides for every barium? 2. So it's going to be Ba, open parentheses, OH, close parentheses, with a 2 on the outside. Now you have a balanced equation. And then we're going to have our arrows, which are going to be two-way arrows, because this is a neutralization, and neutralization goes back and forth. And then our acid becomes our conjugate base, our base becomes our conjugate acid. And the way they do this is by giving away hydrogens. So let's go ahead and write it out. So we're going to have, so barium bromide, Ba, Br2, plus H2O. And then if we wanted to balance this equation, we would put a 2 here, and then our equation's balanced now. Just make sure. Yeah, it's balanced. No, it would be 2H2O, and that's it. Now it's balanced. But if you didn't balance the equation, it's not a big deal. You won't see any questions on the ACP that ask about balancing, but you will. Ideally, it would be a balanced equation. So this is it. Hands up if you got this exactly. Okay. Hands up if you got this, but without the 2's. Without the 2's that I just erased. All right. So if you got this, then you're good. But having it balanced, of course, would be ideal. Just so you have the same number of things on both sides. Say it again. Yeah. Yeah. All right. Let's keep going. So identify the following conjugate acid-base pairs. So I'm going to give you guys, let's do 6 laps, and then we'll go over these. All right, let's go over these real quick. So here in this one, we have H2O. What does H2O do? It gains. So what does that make H2O? So here's a base. Here's our conjugate acid. Here's our acid. And then here's our conjugate base. Like, it's very simple. You find out what one thing is, you can figure out everything else. All right, next one. H2O does what? It gains. What does that make it? So base, conjugate acid, conjugate base, and then acid. Over here, we don't have water, so let's just look at our acid. So HF turns into F minus. So what is HF? That's going to be our acid. Here's our conjugate base. And then here we're going to have our base, and here's our conjugate acid. And then this last one, we can look at any one of these. So HNO2 becomes NO2. So what is HNO2? Acid, conjugate base, and then here we have our base and conjugate acid. And that's it. Any questions on these?
Why is the conjugate acid for
Say it again.
Why is it conjugate bases for 3 or 4 different reasons? Just because they don't have the water?
So here's what a conjugate base is, in case y'all are wondering. A conjugate base and a conjugate acid, it just means if you flip this reaction, which one is going to be the acid, which one's going to be the base. So let's flip this reaction. So F minus plus H2SO3 is going to yield, HF plus HSO3 minus. All right, so if we flip the reaction, because it's a two-way reaction, what's happening now? So fluorine is doing what? It's gaining. So what does that make fluorine? Base. And this is going to be our conjugate acid. And then over here, what's H2SO3 doing? It's giving a hydrogen, which means what's it doing? What is it? There's our acid. Here's our conjugate base. So all conjugate means is if you flip this reaction, what's going to happen? What are these things going to do? So your conjugate base is your base in that scenario. So if you flip the reaction. Yeah. You can do that too, yeah. So usually your base is going to have a negative charge. That's one way of identifying it. And your acids, you're gonna be able to recognize them. But anytime you have a negative charge, know that's your base. Anytime you have a positive charge, that's going to be your acid. Even though we don't, go ahead. For number 2, if we weren't looking at the other side, if we were just looking at this, how do we know what's what? So let's ignore this and then just look here. So over here, I know, yeah, it does look like it is negatively charged. But yeah, in this scenario, it would be really tough. But
okay.
Yeah, so in this scenario, the only way to do it would be to look at your conjugates. But you're not going to see questions like that. So in order to answer a question like that, you just have to know that water is more acidic. It's more basic than this stuff. Even though, so in this scenario, really, this is a base and this is a base, but this one is more base. And because this one is more base, this one is acting like an acid. Like that's what's happening here. So think of it as a spectrum. Which one is more acidic? Which one is more basic? And that's just how the pull works. For example, here, so sometimes water is an acid, sometimes water is a base. It just depends on what you're mixing it with. Any other questions? All right, so